All right, our next speaker is Dongjae, and Dongjae is going to be presenting us fair operational semantics.
Hi, can you hear me? Okay. Yep. Hi, I'm Dongjae Lee, and thank you for attending this talk. Today, I will introduce fair operational semantics, a joint work with these amazing collaborators. The main topic of this talk is fairness in program verification. To begin, I would like to point out that programmers usually take it for granted that the systems they work on is fair. For some examples, when writing a concurrent program, one usually assumes that every thread is eventually scheduled, every thread trying to acquire the lock eventually succeeds, or network requests are eventually processed, or even weak memory is eventually updated, and more. However, in the context of program verification, formal ways to express and reason about fairness is underdeveloped compared to, say, safety. We tackle the status quo by developing fair operational semantics, a general and principled approach to fairness, which is both expressive and provides powerful proof techniques. I will introduce our work step by step, first introducing what fair operational semantics is. To give some intuitions, I will use this simple concurrent program as a learning example. This is a simple message passing program between two threads, where thread 1 passes value 3 to thread 2 by writing to a shared memory location, x. And thread 2 waits for the value in a do-while loop. And also note that this program uses a blocking lock to avoid data races. Thus, a thread can be blocked before it acquires a lock. Now, we naturally expect this program to terminate, and the reasoning behind this goes like this. First of all, we assume that both threads will be eventually scheduled. Next, we assume that both threads will eventually acquire the lock, which in turn means that thread 1 will write 3, and thread 2 will read it. Finally, both threads terminate, and the entire program terminates. However, we can see that there are some crucial assumptions we made to justify the reasoning. First, we assumed what we call scheduler fairness, which says that thread 1 and 2 will be scheduled. Second, we also assumed what we call lock fairness, which says that thread 1 and 2 will acquire the lock. Indeed, it turns out that this program can fall into an infinite loop when these assumptions are not met. For now, let me focus on scheduler fairness and postpone lock fairness for a later discussion. To illustrate how an infinite loop is possible, I will introduce these gray triangles to indicate the line each thread will execute when scheduled. Then we also have a purple triangle, which indicates the current line of execution. Then a trivial scenario is when the scheduler only schedules thread 2, in which case we start from thread 2, and it acquires a lock, reads 0, and releases the lock, and loops back, because the loop condition is true. Then the same execution goes on forever because the scheduler only schedules thread 2. As this example shows, an unfair scheduler can give unexpected executions. This motivates us toward a property of schedulers called scheduler fairness, which simply states that every thread eventually gets scheduled. Then, as the previous example showed, we want to assume scheduler fairness in order to formally verify that programs behave as we expect. But then, how can we formally express this assumption? Actually, it turns out that we can get some key intuitions by taking a look at some unfair executions. So I will show you some unfair executions using this table and these symbols. The tick mark indicates that the thread is scheduled, and the cross mark means that the thread is not scheduled. So let's express our previous unfair execution where only thread 2 is scheduled using these marks. First, thread 2 is scheduled, so we write down the tick mark for thread 2 and the cross mark for thread 1. Then thread 2 is scheduled again, giving the same event. And you can see that this continues forever. As a result, only the cross mark continues infinitely for thread 1. And our key observation here is that an unfair scheduling for thread 1 means thread 1 is infinitely not scheduled. We formalize this observation by defining the fairness event, which can be a good event or a bad event. Here I is a thread ID for which this event is triggered. Then fairness event captures the concept of fairness with its unique semantics called fair operational semantics, or FOS in short. It simply says that for each thread ID, triggering bad events infinitely without a good event is not allowed. Then with FOS, we can express scheduler fairness formally. In fact, all we need to do is to invoke the good event for the tick mark and the bad event for the cross mark. Then the previous scenario, where only thread 2 is scheduled, triggers the sequence of fairness events shown in the table. You can clearly see that thread 1 gets infinite bad events without a good event, and therefore, this scenario is not allowed under FOS. In other words, what FOS ensures is that a good event will eventually happen for every thread during an infinite execution. So under FOS, only fair schedulings, like this one, is allowed, and FOS does this by ensuring that a good event eventually happens for each thread, which in this context means every thread is eventually scheduled. So FOS expresses scheduler fairness in a simple yet elegant way. But of course, this is not the end of the story. It turns out that FOS can express various concepts of fairness, not only scheduler fairness. To do so, we first slightly generalize the previous definition and allow the fairness event to distinguish between different kinds of fairness events by taking it as a parameter. Of course, the definition of FOS is updated accordingly. For example, in the case of scheduler fairness, we use a fancy S to notate that the kind of fairness considered here is scheduler fairness, and modify the previous events. Now, I will demonstrate another kind of fairness called lock fairness. Actually, it is already crucial for our running example, and I will demonstrate why from now. To focus on lock fairness, I will assume scheduler fairness from now on. So let's take a look at a possible execution of our running example. As we did for the scheduler fairness, I will use symbols to visualize the execution. This time we have the lock symbol to notate that the lock is acquired, the key symbol to notate that the lock is released. We also have the angry face, which means that some other thread took the lock, which a thread is waiting to acquire. Then let's play the same game as before and write down the symbols on the table along with an execution. We start from thread 2, which acquires the lock, getting a lock symbol, while thread 1 getting an angry face. Then thread 1 is scheduled and tries to acquire the lock, but it fails because it is blocked. And we come back to thread 2, which reads 0. Thread 1 is scheduled, but again blocked. Then thread 2 is scheduled, releases the lock with the key symbol, and it is scheduled in a row, again acquiring the lock. And as you can see, thread 1 is scheduled, but again blocked by the lock. Now this can continue forever, which means that even we have a fair scheduling, if lock acquisition is unfair, we can still get an infinite loop. Then how can we capture the assumption that lock acquisition is fair? The essential intuition is captured by the definition of lock fairness, which states that if every thread releases the lock, every blocked thread eventually acquires the lock. And indeed, lock fairness captures the condition for our running example to terminate as we expect. To illustrate this, let's carry out the same game as before and fill in the table. We start from the same scenario, and thread 2 is scheduled first and acquires a lock, and thread 1 is blocked. Then thread 2 reads 0, and thread 1 is scheduled, and again blocked. Then thread 2 is scheduled and releases the lock, and scheduled in a row and acquires a lock. Now this can go on, and thread 1 can get many angry faces. But this time, lock fairness guarantees that thread 1 eventually acquires a lock, and thread 1 can make some progress. All in all, under fair scheduling and fair lock acquisition, we can finally prove that this program eventually terminates. Now encoding lock fairness using FOS is simple, similar to what we did with scheduler fairness. We encode such that the lock symbol triggers a good event, and the angry face triggers a bad event. Then FOS ensures that only finite bad events occur before a good event, so each thread gets only finite angry faces in a row. So visualizing this would look like this, where if thread 2 acquires a lock, thread 1 gets a bad event, and this can go on. But as some finite bad event, after some finite bad events, thread 1 is guaranteed to get a good event by FOS. So it is guaranteed to acquire the lock. So I gave 2 examples on the expressiveness of FOS, which is scheduler fairness and lock fairness. However, it turns out that FOS can do much more, and we show various examples in our paper, such as scheduler fairness, progress properties of concurrent objects, such as lock fairness, starvation and deadlock freedom, strong and weak fairness, and readers and writers problem, and even weak memory fairness. Now I would like to turn our attention to how we actually prove things in FOS. So we have our running example, and we want to prove termination of this program utilizing scheduler fairness and lock fairness. First thing to notice here is that we can now prove that the loop terminates. Why is this so? Because we have scheduler and lock fairness, which guarantees that the loop will eventually terminate. This leads us to the core proof principle, namely that fairness enables performing induction to prove termination of loops. But FOS in current form does not provide something concrete to perform induction on. What we want is some kind of number to carry out inductive reasoning. Thankfully, it turns out that we can rephrase the definition of FOS to obtain a natural number to perform induction on. So FOS ensures that no infinite bad event without a good event occurs, which in turn means that FOS ensures only finite number of bad events before a good event. Therefore, FOS actually provides a concrete number we can work on, which we call the fairness counter. And for brevity, I will use this euro symbol for the fairness counter from now on. Then, counters are updated in a simple way. If a bad event is triggered, the counter value decreases by 1. On the other hand, if a good event is triggered, the counter is reset to the number of upcoming bad events. In some sense, fairness counter prophesies the number of upcoming bad events, which is made possible because FOS ensures that only finite bad events happen before a good event. Then one can see that the fairness counter can indeed be used in proof by induction. Let's see what happens when this loop iterates, and for each iteration, a bad event will be triggered by either the scheduler fairness or the lock fairness, and decreases the corresponding counter. So we now have our main proof technique, which is to do induction on the fairness counter. However, the actual reasoning we need to do is much involved. In fact, termination of the loop in thread 2 is a result of a non-trivial combination of 3 components, which are scheduler and lock fairness, and the fact that thread 1 releasing the lock. But this mixture of reasoning is where FOS really shines, because we can combine fairness counters in a straightforward way and also take in techniques from program logic. And finally, the reasoning we have to carry out boils down to doing induction on a tuple, which looks like this. I won't explain this now, but you can find details in our paper. To summarize, FOS provides powerful proof techniques. It offers a stepwise reasoning principle on top of which we develop a simulation relation for termination-sensitive refinements and a thread local simulation relation, which is abstracted further thanks to the power of concurrent separation logic. And they are unified proof techniques, and they can be applied to any concept of fairness definable in FOS. And at the end of the day, FOS is a unified approach to fairness, and our flagship example shown here demonstrates the benefits of FOS. Using FOS, we can express multiple kinds of fairness at once, for example, scheduler and lock fairness. Also, it allows us to compare 2 programs with different concepts of fairness, such as one with lock fairness and the other with weak memory fairness. Finally, common proof techniques allows us to prove an end-to-end example like this, which involves 3 kinds of fairness. And the full development has much more interesting results. For example, we present formal definition of FOS, which is a mixed co-inductive, inductive, co-inductive definition. It's difficult one. And we present fairness logic and examples, and our results are mechanized in the proof assistant, and we instantiate the iris proof mode for better proof experience. This is the end of talk, and the slide contains a summary of contributions. We define FOS and demonstrate expressiveness of FOS. Then we also develop proof techniques for FOS. This QR code leads to the project webpage, and thank you all for listening to this talk.
Okay, a reminder that we have a microphone in the middle of the room. If you have any questions, just walk in front of the mic, and then you can ask a question.
Hi, really interesting stuff. I'm Andres Huns from the University of Edinburgh. So the question I have is, I'm curious how this relates to the typical fairness you think of in model checking and temporal logic. Can you comment on, is this easier to work with than temporal logic? Is it equally expressive?
So question was either our approach is easier than temporal logic, like used in the model checking.
Yeah.
So first, disclaimer, I never used model checking, and I don't know much about temporal logic. But I guess the problem really is either it is easier to work with program verification, like in terms of proof assistance, or either it is easier to work with SMT solvers, like all model checkings. And so I can't give you an immediate answer about this, but maybe we can discuss this offline. Yeah.
Yeah, that sounds interesting.
Yeah.
Thanks.
Just one question and comment. So you assume the log fairness, but it depends on the log implementation, right? There might be the ticking log will guarantee the log fairness, but spin log will not guarantee the log fairness, right? So can you prove that actually the log fairness holds for ticking log, and also for spin log you cannot prove it, so that you cannot compose. So somehow you're just not assuming fairness, but also you guarantee and proving fairness.
Yes. Okay. So the question was about so the ticket lock is a fair implementation of locks, and spin lock is does not guarantee fairness. So yes, we actually proved that a ticket lock is a fair lock in terms of that it defines a fair specification of locks. And yes, we didn't formally prove it, but we are pretty sure that spin locks does not satisfy this fair specification. So yes, we can also verify fairness of several different implementations.
So in this paper, your definition of fairness is that one good thing will happen, there's no infinite bad thing that can happen before one good thing. So have you considered the notion that maybe a bounded number of bad things happen before a good thing happen, or some number of bad things happen before, and then you need a fixed or a bounded number of good things to happen?
Can you repeat the question again?
So
please?
it's like in some scenarios, you actually need these bad things to happen maybe just up to a bounded number of times. Or sometimes maybe if you want to actually show your program, refine this program, you actually to show good things will happen at least k times, for example. So have you considered these notions of fairness as well?
Okay, that's a really good question, and so it's definitely one of our future works. We haven't really considered it rigorously, but we believe this kind of bounded notion poses severe difficulty on developing program logic that we can work on. But I believe it is a great future work to work on.
Thank you. If there's no question, let's thank our speaker again.